Good afternoon, everyone. Today I'm going to present my paper, Control Flow Integrity for Cost Binaries. I start from the motivation of this work first. So, simple, what is the control flow integrity? So I give a formal definition here is that the control flow execution, the program execution should follow a statically constructed control flow graph. So why we need CFI? So there are following reasons. CFI, on the first hand, is a foundation for other low-level code defenses. For example, it is the basis of software fault isolation, and it can also use for sandboxing untrusted code. And secondly, CFI can also defeat lots of low-level attacks on binaries, including code injection attacks, ROP attacks, and JOP attacks. And finally, and most importantly, CFI is a deterministic approach. It is not based on any probabilistic defense, such as ASLR, that could be bypassed. And the motivation of this work is as follows. So there are many previous work that closely related to CFI. And the first one is about the CFI in 2005, and there are later work in 2009. And there's also a paper in this year's Security and Privacy. It's a CCFIR. So there are also other flavors of CFI, like instruction bundling, which is used by Peacefield and also the Google native client. And there are also CFI implementation in kernel, like index hooks and other stuff like control flow locking and CFI on mobile platform, MOCFI, and some Windows implementation for untrusted code like rings. So most of this previous work requires compiler support or binaries that contains relocation information or symbol or debugging information. And most of them do not provide complete protection. They either leave executables or libraries or loader unprotected. So, and also they have a difficult time balancing the strengths of protection and compatibility with large binaries. So, throughout all our research, we come to the following result. We have designed and implemented robust CFI implementation on large and low-level binaries. We have tested glibc, GIMP 2.6, Adobe Reader 9, and Firefox, and we transformed all the executables as well as the shared libraries used. It is compatible yet strong policy, as shown that we have eliminated 93% of ROP and JOP gadget. It has good performance, 10% overhead on spec 2006, and 4% if we restricted to C programs. So we also have limitations. Since we are using static binary translation, we don't support obfuscated code or malware. So also we don't support runtime code generation such as JIT, and we have implemented for 32-bit Linux and tested with GCC and LLVM. The key challenges are 4 parts. The first challenge is disassembly and static analysis of cost binaries. Since we have no other information such as symbol table and relocation, these are the 2 difficulties that we have to overcome first. And also the robust static instrumentation that shouldn't break low-level code and shouldn't break transparency for position-independent code or C++ exceptions. Also, we need modular instrumentation that applied uniformly to executables and libraries, and make sure that shared libraries, when transformed, is also shared. So also the key challenges is that there is lack of access to the compatibility and the strength trade-off. So we will show how to solve these issues. The first issue is the disassembly error. Disassembly error can be classified into 2 parts. The first one is the disassembly of non-code. So this can be tolerated by our instrumentation by leaving the original code in place, untouched. And the second situation is the incorrect disassembly of legitimate code. And there are 3 sub-cases for that. The first one is instruction decoding errors, which is not really a challenge, because currently the disassembler can do a good job when decoding the instruction in the x86, such a mature ISA. However, the second issue really causes problems, which is the instruction boundary errors. It is harmful that we show how we solve it using our disassembly algorithm. And third one is failure to disassemble, which can be solved by using the linear disassembly. And the following shows our algorithm to solve the instruction boundary issues. There are 4 steps in this algorithm. The first one is we do a linear disassembly for all the code in the binary. And the second one, we comes to this error detection part. We detect errors based on the observation of the 3 parts. When we find invalid opcode, when we find indirect we find direct jump and call goes outside of module address, and also if we find any direct control flow that goes into the instruction. So once we find anything like that, we come to the error correction part. We identify this data, this gap in the middle of code as following. We scan backwards first to the preceding unconditional jump, and also we scan forward to the next direct or indirect target. The indirect target can be obtained from the static analysis, as we shown afterwards. When this gap is marked, we come to the step 4 and repeat until no more errors happens. So after the disassembly algorithm, we come to static analysis. So why we need to do static analysis? There are 2 reasons. The purpose of doing static analysis is to find all code pointers. And these code pointers are needed for 2 reasons. First, it is used to correct disassembly errors, as mentioned before. Secondly, it is used to construct constrained indirect control flow targets. And this is the basis of our CFI implementation. We classify code pointers into following categories, while we focus on the discovering mechanism on the first 2, the code pointer constant and the computed code pointers. For code pointer constant, we use a simple techniques. We simply scan the binaries for constant that satisfy the following, constant that at any bytes offset within code and data segment that falls within the current module or point to a valid instruction boundary. And for computed code pointers, actually we do not support arbitrary code pointer arithmetic, but we focus on jump tables specifically. In particular, we use a backward analysis mechanism. We analyzing starting from the indirect jump instruction and goes backward in the fixed window size to discover all the arithmetics that involve this code pointer. So after static analysis, we come to binary instrumentation. The following shows that the format of our transformed ERF binaries. Simply, we disassemble the binary. As mentioned before, we transform the binary and assemble it and put the new code and new data into the end of the ERF file. At the same time, we make the original code unexecutable. However, this kind of translation style will cause problems. We have to translate in function pointers, because those function pointers appears as constant in the code, and we have no way to know whether it is really a code pointer or simply an integer. So it cannot be statically translated. So we used a solution from the dynamic binary translation, such as Dynamo RIA and ping. So we do runtime address translation. Also, this kind of instrumentation requires full transparency, which means that all code pointers, including dynamically generated one, such as return address, should targeting only the original code. And this is important for supporting unusual cases for code pointers, such as also it is important to handle those cases to compute data address, such as big code and data embedded in the code. Also, it is useful for C++ handling. Our static binary translation for CFI has the following goal. We need to constrain the branch target to those determined by the static analysis. For direct branches and calls, there's nothing need to be done because all the targets is there in compile time. For indirect branches and calls, we need to check against the table of valid target. This table is constructed statically. And the key observation is that we can combine these 2 things together. We can combine CFI enforcement and with this address translation. So that will be great for us. Our instrumentation is modular. So we show in this slide how we do this modularity. whenever we see so we transform any indirect control flow instruction, such as indirect call shown in this slide, into a push and jump instruction. This jump is a direct jump with the target to a routine called address translation routine. And here is call lookup. So this address translation routine will refer a translation table called MTT1, which maps original address with translated address. Therefore, it further redirect control to the corresponding place in the new code. And the return will be done in a similar way, but using another address translation routine and another mapping table. So, however, a natural question comes out. What if the target is out of the module? So this graph shows how we handle inter-module control flow transfer in a general way. So basically, the first step is the same. An indirect call is transformed into a push and jump will redirect control to the call lookup routine in the source module. And this call lookup routine will have one more step to do. So it will add a rand check where it will check whether the target falls within the local module. If it is not, it will further redirect control to a global lookup routine called call lookup global. And this global lookup routine will refer a global translation table. This global translation table will contains a mapping of the target page address with the address of the lookup routine in the target module. Therefore, it naturally transfers control to the lookup routine in the target module. In this example, the libc. So that lookup routine in libc will further transfer control to the target, and return will simply be done in a similar way, but in a reverse direction while using another global lookup routine. So this GTT table is updated by the loader. So when we intercept the library loading function in the loader, so that every time a library is loaded, this GTT table is mapped. Whenever a library is unloaded, and this table will be updated accordingly. So using this mechanism, we show that we naturally defeat the code injection attacks because the global lookup routine, global lookup table only maps code. So therefore, any hijacked control flow transfer that transfer control to the data will fail in the global lookup routine because it will, look up the GTT table and find nothing there. Then it will crash. And also, the GTT table is initialized by the loader too. So we also instrument the loader to make sure our code is running before any other user code. So after binary translation, we come to our CFI properties and metrics. So the most basic well-known version of CFI is the following. It specifies that return should target next of call. And indirect call and indirect jump should target any function whose address is taken. This is well known. This is obtainable from relocation information, so we regard it as reloc CFI. Similar things has also been implied, described in the Abadi CFI paper in 2005. However, these techniques cannot be applied to cost binary because cost binary doesn't have relocation information. How to cope with this issue? We use a static analysis to over-approximate the function address that has been taken. And now then we come to strict CFI. We call it strict CFI. Unfortunately, strict CFI cannot handle lots of special cases in the real-world program, such as the following. The return might be served as indirect jump, such as the lazy binding in the loader. And also special return may go to function entries in some library functions. Also, return may not just go after call. And also, there are other cases like call may use as a get PC addresses. That is commonly known in position independent code. And also, jumps may be as a replacement of return so that jump may fail. So in order to handle these complications and these detailed corner cases, we come to our own CFI policy. As shown, we have relaxed our policy so that the return address could not just targeting the return addresses RA, but also the EH and CK and CC. So we do that there are reasons that we do this. So, and the brackets shows that. So also, since indirect jumps could be served as equivalent of returns, we share the policy for return and indirect jump. On the other hand, the indirect calls might also have problems. It may also targeting CK and CC. In particular, the PRT jumps. What I mean is like the indirect jumps in a compiler-generated section called PRT section, which is normally used for library calls. Unfortunately, it should normally transfer control only to the exported symbols addresses in the library. Unfortunately, recent glibc feature allows an exported function address to be dynamically loaded at runtime. So we have to compromise our policy for PRT jumps. Therefore, we have to share the indirect call and PRT jumps in the same policy. So, and also the question comes, so since we have to do so many relaxations for this policy, people may ask me why, so you can handle cost binaries, large cost binaries, but is it policy still effective after so many relaxations? So in order to answer this question, we introduce a metric called average indirect target reduction, short for AIR. And how to compute AIR is illustrated in this formula. So in particular, Tj represents the number of possible targets of the J's ICF branch or ICF cause. S represents all possible target addresses, which is the size of binary. So 1 minus the modulo of Tj divided by S represent the indirect target reduction for each individual in ICF instructions. And AIR is simply an arithmetic mean of all of them. So why AIR makes sense? So AIR is actually a general metric that can be applied to evaluate many other control flow containment approaches. So therefore, it can also be applied to measure these two comparatively weaker CFI implementation. The first one is bundle CFI, we call it. It specified all ICF targets should be aligned on 2 to the power n byte boundary. When n equals to 4 is pSphere implementation. When n equals to 5 is Google native client. Also, this can be applied to instruction level CFI too. And this is the most basic CFI, which specified all ICFT targets should only goes to instruction boundaries, which this implementation only prevents jump in the middle of instruction. And now we will show that quantitatively our evaluation using AIR metric. This table will illustrate two things. The first one is that the loss due to use of static analysis is negligible. As you can see from comparative data of strict CFI, which use static analysis, compared with the reloc CFI that use relocation, and the average of AIR is almost the same. And also another thing we can see from this data is that the loss due to Bing CFI relaxation is very small, as you can see from Bing CFI and reloc CFI. And the actual loss of AIR is around 0.2%. Finally, we come to our evaluation section. We have to do 3 things to evaluate our implementation. We first do disassembly testing. We test our several large programs using, we test our code using compiler-generated assembly. Basically, we intercept a GCC linker and assembler so that we can get a compiler-generated assembly, and we compile it with our disassembly, and we find there's no errors. In total, we have checked 5.84 million instructions, which resides in the 58 megabytes of code. In addition, we have done a lot of real-world program testing. We did Firefox 5. We turned JIT off. We opened some, web pages, and we find that there's no problem for that. And also, we do Adobe Reader 9. We open 20 PDF files. We do lots of simple things like scroll, print, zoom in and out, and we find no problems. And GIMP 2.6, load a picture and do some basic operations. Wireshark is my favorite. I transform all the share libraries in the executable, including loader, and I run it and capturing the package on the lane for 20 minutes. There's no problem. Everything works well. And Lix is a LaTeX editor. I open a not large, just I open the report to my professor. I wrote to my professor and do it, edit it, and convert it to PDF. DVI or PS format, there's no problem. Finally, we do a MPlayer and play a song. In total, we have tested 12 real-world programs, and include these 12 programs includes 786 libraries and over 3,000 megabytes of code, and we don't find any problems of that. Also, we shows that we have eliminated vast majority of gadgets, and we have achieved a comparable gadget elimination rate compared with Relog CFI to show that the similar strengths can be maintained while we scale our techniques to large binaries. On average, 93% of the gadget has been eliminated. So that's what we can see from the spec CPU 2006 benchmarks. Since we're doing address translation, which I already shown you that inter-module control flow transfer may have really large overhead since there are so many redirections. So we come to our optimization part. In particular, we have done 4 kinds of optimizations. The first one is branch prediction. We use optimized translation of calls and returns to avoid indirect jumps instead. So also we optimize jump tables. In particular, whenever we see a indirect jump with target or with operand that has a base, index, and stride, we simply transform the corresponding data areas into our own version, and we simply change the base while we sandboxing the index value. By doing so, we could avoid at runtime address translation for those indirect jump instructions. So in addition to that, we also have transparency optimizations. We avoid translation for returns by doing checking, so it's better. And also we do dynamic optimizations for returns too. We do some kind of profiling and make a fast check for most frequent targets. And this picture shows how much we achieved by adding each optimizations. As we can see that we have add branch prediction, we reduced overhead from 26.81 to 13.51. And also we have jump table optimizations, and this is especially good for those programs such as Perl and zhang, which has lots of jump tables. And then we go to transparency optimization. Finally, we achieve 4.29% overhead. So, and yeah, with that, I will take questions. Thanks.
Step up to the microphone stand and state your name and affiliation.
Hi, Ian Goldberg, University of Waterloo. So early on you had in the static analysis section when you were reducing that gap, you had one step where you scanned backwards through the instructions. How do you do that on an x86? Because that's not unique.
We do that by scanning backwards to those indirect, those assembly instructions, and yeah.
But if you're at some place in the byte stream of instructions, how do you know where the previous instruction starts?
So currently, for disassembly, we do not guarantee that this unconditional instruction has been discovered, but there is no problem that we do not find the beginning of data, because So the beginning of data, so our instrumentation may tolerate that. The beginning, some data may be incorrectly disassembled as code because the program control flow won't touch that area. So, however, our algorithm could for sure detect the end of data and the beginning of the code so that there's no instruction that will be misidentified as some other instructions. But for the gap beginning, we do not guarantee it is correct. That's what we have right now. Yeah.
Crispin, Microsoft. It's very interesting that you said that you eliminated 90-some% of gadgets. Are the remaining gadgets still Turing complete? Because that would seem to allow the attacker to ROP the program anyway.
So far as we find, I don't think that is Turing complete. So mostly the gadgets remained are function epilogues, mostly. So most of them are actually useless because function epilogues such as pop and return is simply a jump in ROP.
So the conditionals are missing.
Yeah. So there's no Turing complete so far as we discovered.
Thank you.
Yeah.
This is Eric Bodden from Fraunhofer SIT. I was wondering about the modularity of your approach. So you said that you basically have this compositional instrumentation approach. I was wondering what happens if I load a binary that itself loaded some library that has not been instrumented with your tool. So
yeah, that won't happen because our loader will specify I only load binaries in our own trusted directory.
Okay, so you do assume that all the libraries have been previously instrumented?
Correct.
There's
all the libraries
no way
has been translated in advance.
Okay.
So that any libraries that loaded, which is outside of the range, which won't be loaded by our loader. Right.
Okay, thanks.
So a quick question from me while the next presenter is connecting here. JIT support is one of your limitations. But at the same time, we know that for drive-by attacks, for instance, browsers, as well as most recently Java, which seems to have had like a 0 day in the last, seemingly every month in the last several months, are vulnerable, right? So what are your thoughts on JIT support? How much of a limitation is that?
Yeah, JIT support can also be, actually, there's the question is not in principle level, it's actually in the implementation level. So far as I see that there are some, also there are static binary rewriting that support JIT, which is, I think is a PRDI paper that use native client approach. Their approach is to change the JIT code engine, code generation engine, by generating bundled instructions so that any indirect control flow instruction could only target in safe places. So by doing so, they applied their work, their static binary rewriting work, as some runtime, checking routine, and they applied to JavaScript engine V8, and they also applied it to Mono. So we do not believe there's any principal issues. And I believe this also can be done if we can do it reliably in binary level. And yeah.
Okay, thank you.